Good morning. Our team is formed by Marco, Juan, and Jaques, and today we'll be presenting the design, construction, and preliminary evaluation of a vascular phantom for Doppler ultrasound, focused on simulating healthy and aneurysmal blood flow. In the initial stages of the project, we explored several materials to simulate the mechanical and acoustic properties of human arteries. First, we tried alginate, which was easy to mold but too rigid, making it unsuitable for simulating vessel dynamics. We then moved on to PVA cryogel, a material often used in phantoms due to its adjustable stiffness. However, under ultrasound, it was only visible in Doppler mode. We couldn't see the vessel in B mode. For the aneurysm structure, we used TPU, thinking it would provide a flexible bulge. Unfortunately, it completely blocked the ultrasound beam due to high attenuation. So we'll redesign the model using silicone tubing, which is soft, flexible, and ultrasound compatible. To simulate the aneurysm, we'll localize heat to expand the silicone tube in a controlled way. Finally, we'll surround the vessel with a tissue mimicking gel made of gelatin, laxative, and cornstarch, aiming to replicate the softness and density of real tissue. This combination will give us the best compromise between structural integrity and ultrasound visibility. For our first functional prototype, we decided to use PVA cryogel for the vessel walls. PVA, as I mentioned, is a well known material for ultrasound phantoms because its mechanical properties can be tuned by applying freeze thaw cycles, making it stiffer or softer depending on the application. For the aneurysm, we used a soft TPU segment, expecting it to form a sock like bulge that will still allow ultrasound transmission. We thought this combination would give us realistic elasticity and allow us to observe flow disturbances in Doppler mode. The choice of materials was based on their flexibility, acoustic potential, and ease of shaping. Our main goal at this stage was to build a stable mode that could show both normal and pathological flow on conditions in ultrasound. And as I have here all the specification and characteristics for our phantom for the aneurysm. For our latest Phantom model, we started by 3D printing a mold using PLA, which served as the external shell to shape the Phantom. The aneurysm itself was printed separately in TPU, which is a flexible material chosen to replicate the dilated segment of the artery. Once both parts were ready, we bonded the aneurysm to silicone tubing using adhesive, which provided a quick and tight seal. We then prepared a PVA solution by dissolving PVA powder in boiling water, adjusting the consistency based on texture and viscosity. The hot mixture was poured into the mold, and the phantom was subjected to freeze thaw cycles, frozen for 12 hours, thawed for 12 hours. We repeated this cycle several times to gradually increase the stiffness of the phantom, simulating the mechanical properties of arterial walls. Finally, we connected the Phantom to a peristaltic pump using TPU couplings, which we also designed and printed. These fittings allowed us to create a closed loop flow system for Doppler ultrasound testing.
As we can see in this Doppler image is that for healthy part that is represented by the little ones and surrounding image, we obtain a partially flow image. Since we cannot distinguish completely the size of the dot, we ask if this was a problem of the material of the dog, the material of the phantom, or it was a problem to take the image. Continue with the characteristics of the Doppler image, we can see that the change of colors is correctly, since we obtain red colors for high velocities and for low velocities we obtain blue colors. Finally, for aneurysm, that is the condition part, and where is all the information about change in flow velocities, we cannot see anything. This is because the Doppler image is totally attenuated by the material of the aneurysm. The effectiveness of the phantom is affected by the material radius, meaning that the PBI, despite the characteristics that have been reported in several studies, doesn't allow a correct visualization in the true ultrasound mode. This despite to the force exerted during the study, since as shown in the image, The tube is very close to the ultrasound, being the only way in which you can distinguish the upper edge, but without any trace of the lower edge of the tube. This could also be caused by the thickness and material of the tube or also the material of the phantom. For the aneurysm, the use of TPU prevents the capture of a Doppler image, since the image is totally attenuated by this material. Since the phantom does not fully simulate the characteristics of arteries, the aneurysm, and soft tissue, it provides a decent visualization of the blood flow.
Well, let's talk about the limitations we identified in our ultrasound phantom design and how those limitations affected our results, and some proposals for improvement, both for the phantom itself and the evaluation methodology we're using. As mentioned previously, our phantom uses PBS gel as the tissue mimicking material, a rigid industrial PVC tube with a 13 mm inner diameter as the artery, and a 3D printed TPU aneurysm as 10% concentric infill. The blood mimicking fluid was water with glycerol. The first thing we can notice is that during the ultrasound Doppler evaluation, the ultrasound waves did not pass through the aneurysm region, and no color Doppler flow could be visualized. Our theory is that TPU has a high acoustic impedance mismatch with the surrounding phantom materials. This causes strong reflection or scattering of the ultrasound waves, preventing proper image acquisition. Also, the low infill and concentric pattern could have created internal air gaps and multiple acoustic interfaces, which could have reflected the ultrasound beam, so the aneurysm structure is faint and the Doppler flow is not detected inside the aneurysm. Some studies like Antonio et al. In 2021 have showed the promising applications of thermoplastics in the realization of ultrasound phantoms, but it's still very experimental and presents a lot of different randomness. Another of the problems is related to the use of the clear industrial PVC tube. The structure of the artery was barely visible and only partial Doppler flow could be detected. PVC is too rigid and dense, leading to power penetration and strong boundary reflections. It also does not mimic the compliance of real arteries, which affects realistic simulations. Another of the points that could be improved is the blood flow simulation with water glycerol mix. While viscosity was acceptable, there was no scatters in the liquid to reflect ultrasound waves, which degraded the Doppler signal. It can be seen actually that the color Doppler visualization is quite weak and inconsistent. What are we going to do about it? Well, we have a couple ideas. First, we are going to use more suitable materials. We are replacing the rigid PVC and 3D printed GPU with materials designed for ultrasound phantoms, such as soft PVC, PBA hydrogel, or silicone based, which will have tissue like acoustic properties. We will also from now on avoid 3D printed materials for regions where ultrasound transmission is critical, or maybe we will use it but only as molds for casting tissue mimicking gels. We will also try to ensure homogeneous internal structure and eliminate any infill or internal gaps that can create unwanted reflections. If 3D printing is necessary, we will use high infill and acoustically compatible materials according to literature. We will also implement soft silicone or flexible PVC tubing to better mimic arterial wall compliance and ultrasound transmission, while also degassing all material before assembly to prevent acoustic artifacts, with Mitch avoiding bubbles and gaps. Another point of improvement is we are adding scatterers to the fluid, which means incorporating microbubbles, polystyrene beads, or even starch particles into the fluid to enhance Doppler signal. These act as echogenic particles that reflect the ultrasound waves and improve the visibility of blood flow. It would be also useful to optimize evaluation parameters such as the transducer frequency, color gain, and wall feature, and protesting the phantom with multiple configurations, but we don't have time for that, so we will just ignore it. Finally, for our final evaluation methodology, we will control experimental variables. We will always be using the same traducer settings and depth for consistent results. We will also try to validate our results with commercial phantoms available in already made studies, and also document any artifacts and failures by recording and analyzing any imaging for artifacts or limitations for future improvements. To conclude, our current phantom design presents significant limitations for ultrasound imaging, mainly due to material selection and internal structure. The ultrasound waves are either reflected or highly attenuated by the 3D printed TPU aneurysm and the rigid PVC tubing. This severely limits the ability to visualize both the vessel walls and the Doppler flow. especially in the aneurysmal region, where no flow could be seen at all. These findings suggest that improvement is essential and a must, so we could achieve more realistic and reliable results. We need to switch materials that are acoustically compatible, homogeneous, and flexible, such as PVA gel for the aneurysm and silicone or latex tubing for the vessel. Also, we should refine the design methodology by including proper Doppler scatterers in the fluid and optimizing the evaluation protocol with adjusted ultrasound parameters, if it's possible. In short, a more biomimetic design and better testing procedures will significantly enhance both the educational and diagnostic value of our phantom proposition, so it could be used in future ultrasound simulations.